Well, I guess it's a good moment to start. Let's see. So, what we have talked so far is, well, this last time I more or less gave you the statement of the Poincare conjecture. Again, remember that that just says that, like, if you look at all three-dimensional universes that are possible, basically, um, only what we're calling the three-dimensional sphere will be the one that has this property of being simply connected. Simply connected just meant that if you draw like a loop on your universe, then you can keep shrinking that loop as much as you want without like having to exit your universe. So again, if you remember the donut, the issue with the donut is that you could draw loops that go like around this hole. And those loops, if you want to shrink them as much as you want, like you sort of have to go through the interior of the donut, but like the interior of the donut is in a sense not part of your universe. So that's why we had said that the donut is not simply connected. On the other hand, like the sphere that you know, like the usual sphere, like the surface of the earth, that one is simply connected. It does not have this property about having certain loops that cannot be shrunk to like a point or as much as you want. Now, today, like, so uh, what we're going to do in a way is, I think it's useful for me to give you like an idea of how things are studied. So I already told you like a little bit about like what the objects are, but like like we had this donut torus that's also called like that way. We have the spheres and other things. So you already understand a little bit about the organisms that are sort of out there in nature. But like now, if you were like a taxonomist or a biologist, how would you study the organisms? Like maybe you would try to like look at their DNA to sequence their DNA, right? And so what is like the analog of the DNA sequencing of these universes, right? And by that I just mean what sort of like are like the list of properties or characteristics that could allow you to say, oh, this universe has this property and this universe does not have this property. So what we're going to do today is sort of like start to understand like what those tools are and what are sort of like the properties that like mathematicians or other people would use to like understand those shapes. What we have to do like is first like something that will look a little bit weird. It will look completely different from what we have discussed up to this point. But that you'll see is related in a cool way with we have said. Now, the easiest way to explain this is actually by showing you like a couple of quick videos. So I figured like there's no rule saying why we cannot watch like 5 minutes of YouTube in class. So I think we'll just do that at the beginning of today because that way it will be easier to put the problem into context. So let me see if I can share the video. I mean, there are like the videos that I mentioned on the announcement I created over the weekend. I don't know if anyone's got a chance to see them. If you didn't, that's okay. That's not a problem. We're not going to watch all of them because that would take a lot more time than what I want to spend on the videos. But at least we'll see a couple like some fractions so that you get like the gist of it. So like basically what I'm going to explain to you today is like what the Euler characteristic is, which is something that maybe some have heard before. I don't know if anyone has heard like about the Euler characteristic. Uh, let's see. Good. Can everyone see the Firefox screen?
I can, yeah.
Good. Let's try to. I hope the audio works. Like I don't know when you share, like if the audio also works. So
People living in Conisburg in.
Did you hear that, or you cannot hear that?
Yeah, we can hear just fine.
Okay, and it is you can hear it well. Good. Okay, let's watch this. Like I'll go full screen. Like again, it will be like just like the first 6 minutes of the video. He's kind of funny. Like I will like yeah. Let's do that like to see what he says. Like I think like you will enjoy this video. He's sort of like a fun character. So let's see.
What's now people living in Conisburg in what's now Russian Poland, hard to say which, they had 7 bridges across 2 shores of the Pragal River, and there's 2 islands. One island here, an island over here, there's a bank over here, bank over here, and they've got it set up so that there's 7 bridges. 1, 2, so you could go, you walk over this way. You could take a horse and buggy over to that side, cross over here, and cross over here. 1, 2, 3, 4, 5, 6, 7 bridges. People argued, can you take a Sunday walk and just cross every bridge once? So I want to go out someday and just walk across this bridge, walk across this bridge, walk this bridge. Oh, I'll go this way this time. Walk across here. Oops, I can't do it because I've already crossed those and I've left one. I don't care where I start and where I stop, but can I cross every bridge one time? People argued about it. Nobody was able to do it. Euler's in St. Petersburg working for the Tsars. And he hears about this problem. And up until then, people had said, well, we have to make a list of all possible ways to do this. We have to try here, go there. And in this wonderful paper that Euler writes, he says, trying to solve it one at a time doesn't tell us anything new. It's what today we would call a numerical solution. That might give you an answer, but it doesn't give you understanding. He's saying, how do I do this? And then he says, think about ordinary bridges. Every time I walk across a bridge onto an island, I go from blue to polka dot land. Oh, blue to polka dot land to red, the red shore over to polka dot land. Oh, okay. Euler, rather than concentrating on the bridges, starts saying, look at the islands, look at the land masses. Let's label those and think about that. So he goes over and says, I'll label them. Oh, okay. I'll label what I call polka dotville. I'll call that A. I'll reach in my pocket, call this B over here. Over here, this side, let's call it C. And look at this. There's D. I shouldn't be walking in the water. I should just stay on the. In fact, I can't do that. I ought to just stay on the bridges the whole time. Keep me honest here, Brady. Let's make it real simple. If I have nothing but a bridge going from C to D to B, they start from C to D. Okay, that's legal. So I have CD. They go from D to B. Oh, it's DB. Every time I get from one to another, from one landmass to another landmass, I can make a list of my travels. Oops, stay out of the water. Euler says this means that if I have an even number of bridges, one, going into and out of an island, that's completely legal. I can go right through the island if I have 2, or if I have 4 bridges, I can come across here, back, over, and back. But an odd number of bridges, okay, I can come across here and come across here, but I'm stuck. Go this way, turn around, but I haven't crossed this one. Alternatively, I could start on yellow, on D, walk this way, come back here, and then walk out here. Euler says, oh, if I have an odd number of bridges to any or from any island, I have to either start my walk at that location or end my walk at that location. Right now, island A has 2 bridges going to it. That means, oh, if I do not start on this island, I can just traverse it. You know, Euler goes on and says, and if I start on that island, I can go around blah, 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 and return to it. Even numbered islands, islands that have an even number of bridges going to them, I've got it made. This makes it possible for me to almost eliminate them from my thought process. And it works whether it's 2, 4, or even 6. Okay, got that one. Any land masses, any place that has a bridge connected to it, if it has an even number of bridges, oh, easy, piece of cake. If it has an odd number of bridges, then it's a special case. Clearly, if there's just one landmass that has an odd number of bridges, I can start on it, but I won't be able to get back to it to stop on it. But if I have 2 islands that have an odd number of bridges leading to them, I can start on one, traverse around, and then end on the other one. Now let's go back to what was really happening in Konigsberg around 1725. 7 bridges, remember? Wasn't arranged like this. It was 1, 2, 3, 4, 5, 6, 7. Okay, let me see. Let me see how I'm doing. This section, the red shore, what he calls C, I have 1, 2, 3 bridges from. Oh, it's an odd number. Odd number. Okay, how about D? Let's go over to island D, 1, 2, 3 bridges. Oh, this is odd. How about the North Shore, B, 1, 2, 3, odd number. What about island A, 1, 2, 3, 4, 5, an odd number. All of these land masses have an odd number of bridges leading to them. Euler says, none of them have an even number of bridges. All are odd. No matter where you start, you cannot traverse all those bridges. Along comes World War II.
Okay, I think let's pause for a moment here. Like, I don't know, like I will give you like a brief summary of what he was saying, but like, was everyone able to listen to it? Like, was it making sense?
Yeah.
It's funny, right? So here's like the thing that was happening. So it's sort of like one of these funny things, like we're like almost like by historical accident, like you end up developing, well, not you, like Euler ends up developing like entire branch of mathematics. So like they had this city, right? They have 7 bridges. Like maybe if it had been like 3 or 2 or 1, like it would not have been like a fun game for people to think about. But like, so they have the 7 bridges in the city, and they're like, oh, can we just like do like the Sunday walk in such a way that you only cross each bridge once, right? That was like the challenge. In fact, like I will show you like another video which is a little bit shorter, which explains this. I think maybe in a more succinct way. But like apparently when Euler like was presented this question at the first time, like he thought like, I mean, this is like a silly question, right? Like this is like a beneath a mathematician. Why would I think about it? But like the more he thought about it, the more like interesting it seemed to him. And like basically that's where he like gave birth to what's known today like as like to graph theory and topology, which are like 2 of the most important areas of mathematics, especially graph theory. Probably now everyone talks about social networks and other things, right? All of that is related to graph theory, connectivity. I'll tell you a little bit more about this in a moment. and again, like this may seem totally unrelated to what we have been talking so far. It would be like, I think it would be interesting to see how everything sort of matches in a moment. But like the key takeaway from the video, what he was trying to explain is that sort of like the genius of Euler was to realize that like the islands became like the central focus of attention, and you had to like sort of ask, oh, is it an even or odd number of bridges that are sort of in like going into or outside the island, right? So like like the point is like it made like it was easier to handle the even case, right? Like where like there are like 4 bridges to an island than like the case where there are like just like 3 bridges to a specific landmass. Okay, so that's more or less like with the main distinction. And like again, like I think he was trying to say it at this moment, but I stopped the video. Like what Euler is saying is that in this particular problem of the Königsberg city, like there's no way. What he was saying is like he proved is that there's no way to cross all 7 bridges just once, right? So like what I will show you right now is like another video, which is a little bit shorter, but I think it explains the situation a little bit more quickly. It's just like less funny because he is a funny guy, the one in this video. And then I'll start telling you like some stuff which is more related to what we have been talking to this point. So again, like the next video will re-explain a little bit of what just was said. So let's watch that one first, and then we'll keep discussing it.
You'd have a hard time finding Königsberg on any modern maps, but one particular quirk in its geography has made it one of the most famous cities in mathematics. The medieval German city lay on both sides of the Pregel River. At the center were 2 large islands. The 2 islands were connected to each other and to the riverbanks by 7 bridges. Carl Gottlieb Euler, a mathematician who later became the mayor of a nearby town, grew obsessed with these islands and bridges. He kept coming back to a single question: which route would allow someone to cross all 7 bridges without crossing any of them more than once? Think about it for a moment. Give up? You should. It's not possible. But attempting to explain why led famous mathematician Leonhard Euler to invent a new field of mathematics. Carl wrote to Euler for help with the problem. Euler first dismissed the question as having nothing to do with math. But the more he wrestled with it, the more it seemed there might be something there after all. The answer he came up with had to do with a type of geometry that did not quite exist yet, what he called the geometry of position, now known as graph theory. Euler's first insight was that the route taken between entering an island or a riverbank and leaving it didn't actually matter. Thus, the map could be simplified, with each of the 4 landmasses represented as a single point, what we now call a node, with lines or edges between them to represent the bridges. And this simplified graph allows us to easily count the degrees of each node. That's the number of bridges each landmass touches. Why do the degrees matter? Well, according to the rules of the challenge, once travelers arrive onto a landmass by one bridge, they would have to leave it via a different bridge. In other words, the bridges leading to and from each node on any route must occur in distinct pairs, meaning that the number of bridges touching each landmass visited must be even. The only possible exceptions would be the locations of the beginning and end of the walk. Looking at the graph, it becomes apparent that all 4 nodes have an odd degree. So no matter which path is chosen, At some point, a bridge will have to be crossed twice. Euler used this proof to formulate a general theory that applies to all graphs with 2 or more nodes. A Eulerian path that visits each edge only once is only possible in one of 2 scenarios. The first is when there are exactly 2 nodes of odd degree, meaning all the rest are even. There, the starting point is one of the odd nodes, and the endpoint is the other. The second is when all the nodes are of even degree. Then, the Eulerian path will start and stop in the same location, which also makes it something called a Eulerian circuit. So how might you create a Eulerian path in Königsberg? It's simple. Just remove any one bridge. And it turns out, history created a Eulerian path of its own. During World War II, the Soviet Air Force destroyed 2 of the city's bridges, making a Eulerian path easily possible. Though, to be fair, that probably wasn't their intention. These bombings pretty much wiped Königsberg off the map, and it was later rebuilt as the Russian city of Kaliningrad. So while Königsberg and her 7 bridges may not be around anymore, they will be remembered throughout history by this seemingly trivial riddle, which led to the emergence of a whole new field of mathematics.
Is that okay, everyone? What that video was it?
Yeah.
Interesting, right? Let's see. How do I quit? Okay, full screen. Now this is what I want. Okay. Let's go back to the chat. I mean, like, I suppose, like, we don't really care too much about like the specific solution, like that you could not cross like all the bridge, like that you had to cross one of the bridges at least more than once. Like what I wanted like you to notice, like, it's like this change of perspective, where like Euler basically realized that to like you can abstract a problem and you just think of this, like what this video mentions is like called a graph. So that's where really I want to start with today. Okay, so let me stop sharing the screen, and like basically we were going to start talking a little bit about graphs. Okay, iPhone. Good. So like the idea of if you think about the bridges, right? Like in this Königsberg city or problem, by the way, like Euler, I don't know how much you know about him. I mean, probably like he's the one of like the number E, right, that you use all the time in math. Like, like probably he was like the most like prolific mathematician of all time, in the sense like number of publications and contributions. He also had like 7 or 8 kids. He also became blind, but was still doing math. He was sort of like very interesting figure. So he was very powerful. So again, like think of each of these like dots that I'm drawing as representing one of the 4 land masses, right, in the videos. And then like I'm going to draw edges, right, which represent the bridges connecting the dots or the land masses. So If I did it correctly, that's how this was supposed to look. I mean, I'm just going to call, like, label them, the edges. Like, there's no particular reason why I'm choosing one to be called 1 or the other 3. Like, it's just like to give them numbers. Like, I think I'm taking this like notation from one of the 2 videos. Like, okay. And then let's see. So like what we have here are like this is called the graph. A graph usually you can think of it as just being like a collection of like what's called vertices, edges, and faces. Okay, again, like there's sort of like a more formal definition, like a more rigorous definition, but just think of a graph as being that. And so like in this case, the vertices, right? Like think of them as the dots, right? And in this particular problem, right, we have 4 vertices, right? Like which represents like the 4 landmasses. Now, the edges, right? Think of them as sort of segments that start like, you know, that begin at one, that connect vertices, right? So edges, like think of like edges are almost like intervals, and vertices are almost like the endpoints on the of the interval. So think of edges as segments which connect vertices. And in this case, how many, in this particular case, how many segments or edges we have? We have 7, correct? 7, like the 7 bridges of Königsberg, right? And then the faces, right? The faces are a little bit more interesting to try like to explain. But the faces, like the idea is like, you know, the edges, I don't know if you notice it from the picture, like if you think of this being drawn on the XY plane, these like these edges are dividing the XY plane into sub pieces, right? And so the number of like the faces are like the pieces into which the XY plane is being divided. So number of pieces into which the XY plane is divided. So can anyone tell me how many pieces do you see here, like in this diagram? Anyone wants to give it a try?
So, what do you mean by pieces again?
Oh yeah, like I'm just saying, like, you know, think of this like, think of like the edge, like think instead of thinking of them as bridges, imagine they were like walls of infinite size, right? Like of infinite height, correct? Like just lifting up, like imagine that each bridge represented like a super tall wall, right? So I'm just asking, in how many different locations could you get trapped? Because for example, I don't know if you see it here, that like,
Yeah, I was gonna say 4.
okay, good proposal. Let's think about that. So like, I'm just asking, right, for the number of like places in which you get trapped. So like we could have this one, right, which is A. You could also get trapped on this one, right, like meaning that you could walk here without any issues, but then like you know, like you cannot, like if you want to go where A is, like you have to cross like a bridge or like a wall. So we are considering this different. Good. Everyone went for 4, which is like a very natural thing. C and D. By convention, like sort of like you can think of this like if you want those that are finite almost as continents, right? Or land masses. And like there's the exterior is also considered like a piece of the XY plane, meaning that you can think of this as like think of this as a map somehow. So we would say in this case that there are actually 5 faces because the plane was sort of broke, like, you know, this piece like was broken into 4, like this region enclosed by the graph was broken into 4 pieces, but we're looking at the entire XY plane. So we say that there are 5 just to say like the stuff that's like outside the boundaries of the graph, if that makes sense. So what I'm trying to say is like there's sort of like strictly speaking like a 5th piece, which is here. Is that okay? So
Yeah.
like the outside, like the where you like the outside of the city or like the continents. So in this case, someone was going to say something, or so think of them as like, I mean, like I don't know if you have, I mean, like I like so used to mathematical terminology that like I don't know like how much is like common terminology, but like it's like what we would call connected pieces. Like so this is like number of connected meaning that you can travel on this each individual piece without hitting like a wall. So you can travel on all of the outside without hitting like a wall. You can travel here without hitting a wall, travel here without hitting a wall, travel here without hitting a wall, travel here without hitting a wall. So 5, is that okay?
Mm-hmm.
So we get like 4, 7, and 5. So far, so good. Everyone is okay with this?
Yeah, I think so.
Now here's the cool thing, and this is like where we're moving more towards like how this is related to like what we have talked so far. Euler noticed like an interesting fact about that you could play around with these numbers in a fun way. So these are called again vertices, these are called edges, and these are called faces. Okay, and so you get the word beef. Well, beef, I suppose it would be better pronunciation for that. So let's talk about what beef is, or what like really the other characteristic is of the graph. Well, by definition, the other characteristic is a number of vertices minus the number of edges plus the number of faces. Okay. So to this combination, number of vertices minus number of edges plus number of faces, we call that combination the Euler characteristic of a graph. So so what would the Euler characteristic of this graph be? So we're saying that for this particular example, we have Euler characteristic 2. Is that okay? So far, so good?
Yeah.
Good. Now, let's forget for a second about this Königsberg particular graph. I will get back to it a little bit later. let's do something even easier. Like this is almost like the easiest graph like you could imagine. Let me try to keep using the same colors. So how many vertices? 2, right? How many edges? 2. How many faces?
2.
2 as well, right? Because there's like in this case, it's just like the inside. Well, like I'll I'll try like it's not really that's not what it really measures, but I have to give you a little bit more examples to tell you what it really is telling you in this case. So let's just think about, oh my god, what are you doing this combination? I have no idea, but let's just compute it because Euler told us to compute it and he was a smart guy. So but for now, like, yeah, it's not clear what this is telling you, right? I'm just saying, like, let's just find these computations because again, this like Euler noticed something interesting, and I'm going to tell you what like the interesting thing that he noticed. Is that okay? Oh yeah, that's okay. So far so good. Everyone agree. So I'll tell you a little bit more later what the Euler characteristic really is. So so yes, it's also 2. uh, let's do another example. Four vertices. How many edges? 1, 2, 3, 4, 5, right? How many faces? 3. Beth. What is this number?
2.
2. Anyone is noticing something here? I'm still haven't told you what it tells you, but it seems that we keep getting the number 2, right? Now, what's going on? Again, this is a little bit tricky, and like we're doing like some of like talking about some of the most important math of the last century or like the last 200 years. So like there are like some deep things going on here. It's not like I mean, we're just like noticing a pattern up to this point, right? Like, you know, like we're trying to do like a discovery. So now a graph, like again, like a graph is called planar if it can be drawn in such a way that the edges only meet at the vertices. So what do I mean by this? So let's like what I'm trying to say is like, for example, this is planar, right? Because like if you look at the edges, right? The edges are only touching each other. Like if you want to like the only place where two different edges meet, right, is at these vertices, at these purple dots. Okay. Like I'm saying, like I'm like in the sense that we don't have something that like an edge that's doing something crazy like this, right? Because you know, like if you look at this edge, right, it's crossing, it's intersecting this other edge at this point, but this point is not being regarded as a vertex. Is that making sense?
Yeah.
Okay. Now, like, okay, the idea, in fact, the game is a little bit more interesting than what I just presented it as, because like the question is whether it can be drawn in a way so that the edges do not intersect. So what do I mean? Like, what do I mean by this? Is it okay? Let me show you another cute animation. I'll stop sharing the iPad for a second, like just so that I can show you something fun. Here you are. Okay. So can everyone see this like app called Is This Graph Planar? Good, good. So the quest here is like, you see like here they're giving you a graph, right? Like, oh, I'll draw it for like on my iPad screen. Like well here, like here they're giving you a graph, and the thing is like if you look at this graph, right, it's like, for example, these two edges, right, they're meeting at this point, but this point again is not being considered like a vertex or one of these dots, because like there's no dot drawn, right? I don't know if you can see like the difference between, can everyone see like these dots being drawn here? Like, so like, you know, like the way in which it's drawn, like these two edges are intersecting at a spot that is not a vertex. Is that okay so far so good?
Yeah.
Now, but when we say that a graph is planar, we're actually asking whether or not you can move it around in such a way that it becomes planar. So what I'm trying to say here is that what if you do something like this? Did you see what just happened? I just moved this vertex here to this spot. And now, right, now all the edges, at least on this region, have the property that that the edges like are only meeting at the vertices, right? Is that making sense now? Like I just moved around the vertex. So Now you did that. But you say, okay, but you still have this issue on this other side, right? Like you still have this issue that these two edges are still meeting at this spot, which is not a vertex. And I'm saying, good, no problem. Good. And now, um, once again, the these edges only meet at the vertices, right? Is that making sense?
Yes.
So this actually graph would have been called planar because there was a way to move around the vertices in such a way, like so that you could like end up looking at like something where like the edges did not intersect. And now, but obviously, like the question would be like, oh my God, but how do you know if there's like a way to do this, right? Like, I'm not saying that you can always do this, right? Like there's like actually in graph theory, like theorems or results about giving you conditions for when you can do this or not. I'm just saying that like appearances can be deceitful because it's not, I'm not saying that like the first drawing that you're given is the only drawing that you can do of the graph. But rather that like maybe sometimes you can play around with the drawing a little bit so that it is being now presented in such a way that the graph becomes planar. So when you say that a graph is planar, it just means that the graph can be drawn in such a way that it becomes planar. Not that like maybe the first drawing that you're given is a planar graph. And again, if you, and like, if like, by the way, this is called the Wolfram demonstrations project. If someone wants to, like, you can download this for free if you want to play it with this around. And so like there's a lot of graphs. Like I'll show you the others that they mentioned here, but I thought this one was the easiest to understand. You can play with the other graphs to try to make them planar or not. Like it's a cool challenge. But like if you look at this one, how many vertices did you get? You get 1, 2, 3, 4, 5, 6, 7, 8 vertices. If someone wants to write it, I have it on my notes already. So you have 8 vertices. How many edges do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You get 13 edges. And how many faces do you get? You get 1, 2, 3, 4, 5, 6, and then the outside, which also is a face. You get 7 faces. So you get 8 vertices, 13 edges, 7 faces, and the other characteristic is 8 minus 13 plus 7. So that gives you 15 minus 13, and that gives you 2 again. Okay. So you keep getting 2, even if this graph looks a lot more complicated than the others in the past. So in fact, what Euler proved is that the Euler characteristic of any planar graph is 2. Like, and so let me write this down. So what Euler proved, he proved the following. The Euler characteristic of any planar graph is always 2. And then like you ask, oh my God, how do you prove that, right? the proof itself, like it's an interesting proof. Like there are ways, like I would not be against necessarily like telling you a little bit of how it's proven if people are interested in hearing that out. Like we could do that like maybe next time if you want. I can tell you a little bit of how, like I can at least tell you like the main ideas behind it for why the Euler characteristic is 2 if you want to know what goes into it. Like it's a very slick argument. But this is like still like maybe like the remaining minutes of today, I just want to spend them trying to connect this with other things we have talked so far, because like at this point, again, like maybe this seems totally unrelated to what we have been saying. So if you want, maybe I'll tell you how this is being related, like this can be related to like our discussions from before, if that makes sense. And just like the takeaway of here so far is that like there's this interesting combination of vertices minus edges plus faces, and like the suggestion by Euler is that you should look at this combination. Okay, so far is that okay? Like again, like it's not clear to us right now what that is telling you, but I'm just saying like it looks like that's like an interesting combination of numbers. So far so good. So the takeaway from now, for now, the lesson up to now is the combination vertices minus edges plus faces seems to be interesting. Uh, yes, I can. And great point. By me showing you, I'll show you the Wikipedia example, because like, graph theory is actually not it's one of these things that I actually never think about. So I don't know them at the top of my head, but yeah, Wikipedia has like a nice example of a non-planar graph. So if you want, let's go there and you'll see it. I'll stop sharing then like the screen for a second. Just give me, I won't be reading the chat just for like 2 minutes, like while. Um, can everyone see this graph?
Yep.
That's non-planar. And then you say, okay, but how do you know it's non-planar, right? Because like that's the difference, right? Knowing that's non-planar means that I can never play around the way I played with the other one, right? On Wolf, like the app, to like move the edges so that they would like become like that, it would become planar, right? So it's like saying that something is non-planar is like an impossibility theorem. It means like no matter how astute you are, no matter how many ways you try it, you will never like reconfigure these vertices and edges in such a way that it becomes planar, right? So like obviously when you prove something like that, you have to prove like something like every planar graph has specific characteristics, and then you just show, and those characteristics like presumably are easier to identify, and then you just show that like this graph does not have one of those characteristics. And so like again, like there's a like piece in Wikipedia. If you go to Wikipedia and just type planar graph, if you want to read about it, like it'll tell you like some of those elements that every planar graph must have. But like the idea is that like the graphs like they're like a graph can have subgraphs, and if there's planar, like it must have certain subgraphs and things like that. So I'm just saying, like, there's like a way to like understand planar. I mean, there's a way to understand graphs and what they should have if they are to be planar. And then like you just check that this one does not have one of those properties, if that makes sense. But like for us, like the non-planar ones are not really that interesting at the moment. I'll tell you why the planar ones are more interesting. But yeah, graph theory is like a very like developed area of mathematics, again, because like of networks and other things. So like, you know, like you should, like, for example, if if it's okay if I go back to the iPad, like graphs are they're like things that one calls like abstract graphs, which are sort of like the things like in computer science you would study. So for example, or like for algorithms. So for example, an abstract graph would be somewhere one where like the vertices are like people, right? And there's like an edge, like, you know, like, so let's say Bob and Alice and John. So abstractly, you could think of Bob, Alice, and John as being vertices of some graph. And you would say there's like an edge between Bob and Alice if they know each other. Okay. Or there's like an edge between Bob and John if they know each other. Or, and so like here, they would know each other, but maybe Alice and John do not know each other, right? And so you wouldn't draw an edge between them, if that makes sense. So I'm just saying, like, you can start like many situations that you would not have thought about as graphs, like can suddenly become could become graphs if thought from some perspective. So like you can think of edges as telling you whether a certain relation holds. So again, here in this case, like the edges like indicate that the people know each other. Is that making sense? And but then like you like, and again, like you could imagine like the Facebook algorithms or even the Google search algorithms, right? Like they may have a huge graph or like abstract graph which tells you which are the websites that are the most visited, right? Like how those are connected to others. And then you could start asking questions, well, is that like abstract graph? Can that be represented as a planar graph or not? Or things like that. Maybe that's like an important, like could be a useful question to know, like the answer for, or it could not. But I'm just saying like graph theory is like very useful these days because like of networks and other things. Okay. Yes, yeah, yeah. Data structures. Good, good, good. Yeah, discrete structures and other things like this is very something that people like study a lot, and so like again, like graph theory is a huge area. Not one that I can tell you much about, unfortunately, but it's like I mean, it has many fun surprises, like this thing about the Euler characteristic. If you have never seen that before, like it sort of sounds very like I mean, it's like an impressive thing at like at face value, I think. So okay, but now let me try to start relating this to like stuff that we have talked, like this, like again, like looks like, okay, this like is like a different like seminar, because like we're not talking about anything anything like related to what we had said. But the idea is that sort of you can associate graphs to like universes. That's the key, cool, like the concept. Like, so here's like the idea, like the important idea. You can associate graphs to our universes, or like to these like surfaces that we have been studying, to the 2D or 3D. In fact, it can be of any dimension. Well, I mean, let's say, let's start here. Like you can associate graphs to the surfaces. So what do I mean by this? Like, let's think about like a surface like that we know, which is a cube. So it looks like an ugly cube, but there it is. I don't like how this segments look like. So if you look at the cube, and by the cube, again, I just mean like I don't mean the interior of the cube, right? Like it's like the exterior, like the box itself, right? Not the like the stuff you put inside the box. I mean, I don't know, like if you sort of imagine generalizing this idea of the graphs that we have been doing, like there's almost like the picture itself is almost screaming to you that like there could be like an interesting graph hidden here, right? Like, right. Usually you even use like the word vertex for like here for the cube, right? So how many vertices does the cube have? Is that making sense? How many edges does the cube have? Good. How many faces does the cube have?
6.
6 faces. Am I using the same colors? Yes, I am. If you just go with this combination because you believe now that this is a useful combination, what does the Euler characteristic give you in this case? Cube. Moreover, there's something going on here, right? let's say that like for some reason you say, okay, I'm feeling like I want to do the same cube. Like I'm still thinking about the cube, but for some reason I want to draw more edges, like so on the top side, right? I'm just going to draw some more edges and like a new vertex. So like the top face of the box, right? Like just imagine that you drew that configuration. So now, how many vertices do you have? You have 9 vertices, right? Is that okay with everyone? How many edges do you have? You have, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? Hopefully I counted correctly. Is that okay? And then how many faces do you have? Again, we had before we had 6 faces. We didn't do anything to 5 of the 6. So we had the previous 5 ones, and then we have 1, like, so we had 5, right? And then the top became 6th face, 7th face, 8th face, 9th face, right? Is that making sense what I'm trying to say? Like 5 of the 6 faces were untouched, and then the top face was sort of broken into 4 sub faces. Is that okay with everyone? Good. What's the Euler characteristic of this? We get 2 again. What's going on? Again, the mystery keeps growing. Let's look at our friend, the sphere. I don't know if it's clear what I'm trying to do here. I'm saying like you have the sphere. Well, I actually purchased this on Amazon. See, everyone sees this sphere. So I'm saying like we have a sphere, right? And I'm saying I'm trying to draw a graph on this sphere. And so what I'm saying is like look at the equator, right? Which is like here red. and just color it. Everyone sees the orange. And that, think of it as being broke. I mean, in order to make it like two vertices, like just draw like a dot, maybe here. So here you have a dot, and the other dot that's on the other side, right? So you have these two dots. And so now you see like two vertices and two edges here, okay? And then like the faces, you should think as like the first face as being the northern hemisphere. So all of this becomes like the stuff above one of the like the equator becomes like one of the faces, and the stuff below the equator becomes the other faces. Well, I mean, the way I'm not very, I haven't been very precise. Like, let me just put my chalk back here. I haven't been very precise about the rules of the game. You can keep adding more and more vertices, but you can never have like infinitely many vertices at once, if that makes sense. Like for example, like yeah, I mean, there are some rules like in which you have to draw things. So you cannot just do like crazy stuff. I'm just saying like the way I'm drawing this like is an allowed. I'm going to do another drawing in a moment, but yeah, at least you can never have like infinitely many vertices drawn at once. Like that's for sure. But you could like choose more than two vertices. I'll actually do an example in a second where you have more than two vertices, if that's okay, on the sphere. Like I'm just saying that if you go with this, that you have two vertices, two edges, and two faces, again, like here are like sort of like northern and southern hemispheres. And if you look at the Euler characteristic, you get what? 2 minus 2 plus 2, you get 2, right? Now, there's something else that you could have done, like and I think maybe this is like related to your question about like more adding more vertices, right? You could have something like this. So like, I don't know, like what I'm trying to say is like along the equator are sort of added to more vertices. So what happens here, then you get like 4 vertices. How many edges do you get? You get 1, 2, 3, 4, and this long one. So you get 5. And how many faces do you get? You get the southern hemisphere, which is intact, and then you broke the northern hemisphere into 2 pieces, right? So you get 3 faces. Is that okay? So you get 4 minus 5 plus 3, which is 2. So far, so good. Is that making sense? And now here comes the interesting story. And like I will finish with this mystery today, but and you're saying, okay, okay, this is getting boring. Like we just keep getting 2. We're always going to get 2. And the answer is no. Let's look at our friend that donut to the rescue again. anyone remembers? There was a day in class that I told you one day that you could think of the, like I'll use different colors here just to think of this as different shades of red. But do you remember, like I told you that you could think of the torus as being obtained from like the square circle, right? By you know, taking a piece of paper and then gluing the red segments, right? And then gluing the orange segments. Everyone remembers that?
Yeah.
So, and again, actually you can draw this on the torus. Like I'll try to draw it like next time so that you don't have to look at from this model. But you should literally try to do that. Like imagine taking a piece of paper and coloring two segments red, right? That like everyone agrees that these two segments sort of become, is everyone agreement? Like these two segments just become one edge. It would become like one red edge on the cylinder. Is that making sense to everyone?
Yeah.
And so these two, they look like two segments. They're really just one. By the same logic, if you actually color the other two segments orange on the paper, when you close them up, you just only get to one segment. So they actually become two edges. And what happens with the vertices? If you actually see what's ends up happening with the vertices, like this, again, like imagine on the piece of paper coloring the four vertices, like edge, like corners purple. When you glue them together, like the four dots will actually just match together, and one will be like on top of another. So what I'm trying to say is that there will be, again, I'll try to draw this like in the actual torus on the donuts so that you see it next time. We don't have too much time right now, but you get like only one vertex. And then how many faces you'll get? Well, essentially what's going to happen is that like there's only one face, which is like this face that you see here. So you get one face. And again, I'll explain this again one more time. I just wanted to finish with something that will give you not something not equal to 2. What do you get here now?
Zero.
Yes. Finally. So it's not 2, right? So the Euler characteristic of a donut is 0. In fact, and I mean, I'll revisit this next time. If no, like the Euler characteristic of planar graphs is always 2 for sure. Yeah. In fact, what's I mean, like just as a enticement for what's going, I will explain. Yeah. I'll also explain more a little bit more in detail what's going on here. Yes, yeah. What's happening is like someone had asked me what the Euler characteristic is giving you. Sorry, let me write it. Yeah. If you like, and I'll try to explain this next time. But what's happening is that if you take 2, if you do 2 minus the Euler characteristic divided by 2, that gives you the number of holes of your surface. So like the idea is that, like the sphere has no holes. The torus has one hole. Like this like has 2 holes. Okay, And like the Euler characteristic is like, if you prefer to think about it in like the way in which it's usually written, the Euler characteristic is 2 minus 2 times the number of holes. But there are many mysteries that we still need to unwrap from what I just said. So next time we'll keep talking about this. But I'm just saying the different, like the reason why actually different graphs could have different Euler characteristics is because some graphs represent surfaces like spheres, other graphs represent donuts, and they have different holes, and that's why their Euler characteristics differ. So I'll repeat this next time because we already ran out of time. So, but like this is where it's getting closer to what we have been talking about. So the Euler characteristic is like a way to differentiate the universes. Like, but we'll talk about this more again next time. Okay. So good. I'll stop sharing if that's okay. I'll see you all.
All right, well, thank you. Have a great one.
You too. Bye.